Hello everyone. In this video, I'm going to take you through how to design a disaster recovery solution for an on-premise environment into AWS. We will look at the key considerations, architecture patterns, and the best practices to ensure your DR setup is resilient, scalable, and cost-effective. This guide can also be used as a reference if you are looking to build a DR solution tailored to your organization's specific needs. Whether you are a cloud architect, infrastructure engineer, or just someone curious about cloud DR strategies, this video will give you a roadmap from understanding the on-prem environment to implementing a DR solution on AWS. So let's dive in and set the stage for designing a robust disaster recovery plan that aligns with both business continuity and operational efficiency. This is our agenda for this video. Before we jump into the architecture and implementation details, it's important to understand some key concepts that guide a disaster recovery strategy. First, recovery time objective or RTO defines the maximum downtime systems can tolerate during a disaster before resuming a normal operations. Complementing that is the recovery point objective or RPO, which specifies the maximum acceptable data loss measured in time before a disruption occurs. Together, RTO and RPO are critical metrics that guide disaster recovery planning and help prioritize which systems need to be restored first. Next, we need to assess disaster recovery capabilities. This involves evaluating current on-premise DR systems to understand both the strengths and potential vulnerabilities. Alongside that, workload evaluation helps identify critical applications and prioritize recovery based efforts on business impact. Data criticality and recovery objectives are also key. By identifying the most critical data, we can set recovery objectives that minimize downtime and prevent data loss during incidents. Finally, gap identification and migration planning is essential. Here we determine any gaps in the current DAR setup to plan migration requirements and ensure that the AWS solution enhances resilience effectively. By keeping these concepts in mind, we can design a DR solution that not only meets technical requirements but also aligns with business continuity needs. To design a disaster recovery plan effectively, we first had to take a full inventory of the existing on premise infrastructure. For our case, we identified a total of 22 servers. These are across three key layers of metadata, compute, and mid. In addition, we have a load balancer and rely on Active Directory for authentication. We have a high performance NAS or network attached storage, providing 200 terabyte of shared data across all our nodes. This massive shared file system is absolutely critical for the application. Finally, under integration, we have a few constraints that heavily impact our AWS design. Our databases are hosted on premise and must remain on premises. This is important because it means we need a secure, reliable connection from AWS back to our data center during a disaster. Second, the application relies heavily on its hostname. So it is a strict requirement that we must preserve the consistent hostname for the DR environment to function seamlessly. And a final critical point about the Fred file ingestion is that third-party systems send us data and they have done IP whitelisting. This means our AWS DR point will need to present a static public IP that can be whitelisted by our partners to ensure that data flow does not stop during a failover. With our inventory complete and our RTO and RPO target set, it's time to choose the right disaster recovery strategy for our workloads. AWS offers several established patterns and they fall on the spectrum of cost versus speed. On the lower cost end, with the highest RTO and RPO, we have simple backup and restore. This is where we safely copy data and can recover it after an incident, but the recovery time is the longest. Moving up the scale, we have the pilot light strategy. This means we maintain a minimal version of the environment in AWS, just the core services, ready to scale up quickly during a disaster. Next is warm standby. This involves running scaled down versions of our system simultaneously. This significantly reduces downtime when we switch over to the backup systems. Finally, for the lowest RTO and RPO and the highest cost is the multi-site active-active setup. This runs full-scale active systems simultaneously at multiple locations to ensure maximum high availability. Our plan will use our approach to apply these strategies effectively. To cover our critical applications, these have a strict RTO and RPO of near real time, less than an hour. For our Tier 2, which covers non-critical applications, these are more tolerant with an RTO and RPO of around 4 hours. This strategy allows us to save cost on the less critical systems while investing heavily in the faster recovery mechanism for critical solutions. Here we have the components for each area covering the core components, network identity, and external application ingestion. The compute layer, which covers 22 of our servers, which form our core application stack. We will replicate these using AWS Elastic Disaster Recovery or DRS or with AMIs with launch templates or auto scaling groups in AWS. Our physical load balancer will be replaced by an AWS application load balancer or ALP running in multi-AZ mode. Crucially, our 20 terabytes of high performance shared file system will be handled by FSx for Luster to provide the shared storage application we need. The network components, which are the foundation, is an AWS VPC with public and private subnets across availability zones. Since our databases remain on premises, we must use Direct Connect or a VPN to securely link the AWS workloads back to the databases. We will mirror our on-prem firewall rules using security groups and NACLs to maintain the same access policies. And for external clients, we will use Route 53 failover policy to ensure DNS records redirect clients seamlessly to the DR region. For identity and access, our own premises Active Directory will be replicated or extended into AWS using AWS Managed AD or AD connector. This is absolutely vital because without Active Directory, user login and service accounts will fail. Finally, for external data dependencies, for flight file ingestion, where third party use IP whitelisting, we must deploy a DR endpoint with the same public IP or DNS. This means providing a static elastic IP in AWS and pre-whitelisting it with our partners. We also need to deploy the same file transfer mechanism like AWS Transfer Family for SFTP or a custom FTP server so ingestion can continue during failover. For internal connection and communication, we will ensure our internal API endpoints maintain the same URL via Route 53 failover. If the workloads are critical and requires continuous availability, then the Tier 1 approach is best suited. But if the workloads can tolerate longer downtime and don't need real-time application, then our Tier 2 approach can be used to achieve significant cost savings while still maintaining recoverability. Let's look at each in detail. For Tier 2 workloads such as non-customer facing or lower priority applications, we can adopt a cost-optimized DR design. Here we first create servers on AWS similar in configuration to the on-prem servers and then create Amazon machine images or AMIs or use AWS backup with storage gateway to take scheduled snapshots. These snapshots are securely stored in S3 or backup vaults, and in case of a disaster, EC2 instances can be restored manually from these images within the DR environment. Storage is synchronized using AWS DataSync, which keeps data updated to S3 or FSX on a regular basis. However, it is important to note that if the data is moved to S3, it will take longer to transfer back to FSX during a disaster, and file level security and POSIX permissions will be lost. Whereas if the data is synchronized directly to FSX, all POSIX permissions and access controls are retained, allowing for a faster and more secure recovery. Database connectivity during recovery is achieved through VPN access. This model typically supports an RTO and RPO of around 4 hours, providing a balance between availability and cost efficiency. Now let's talk about Tier 1 workloads, which are mission critical applications, systems that demand high uptime and minimal data loss. For these, we use AWS Elastic Disaster Recovery or DRS for continuous block level replication. The DRS agent runs on on-prem servers and replicates data in near real time to EPS volumes in the AWS staging area. In the event of a disaster, AWS DRS automatically launches EC2 instances in DR VPC, reducing recovery time to less than an hour, or sometimes in a minutes. Shared NAS storage is handled using AWS DataSync, which continuously syncs deltas to FSX for Lustre, typically every 15 minutes, ensuring data consistency. So database connections are established securely via Direct Connect or VPN, providing low latency during failover. So in summary, Tier 1 gives near zero downtime through near real-time application using AWS DRS. Tier 1 delivers a cost-effective recovery through scheduled backups and AMI replication while keeping data security intact when using FSX. Now let's take a deeper look at how both strategies differ in cost and what AWS services actually contribute to this cost. Starting with Tier 2, which covers non-critical workloads, this approach is designed for cost efficiency. You don't maintain live standby infrastructure, instead, you only pay for storage and minimal application services. The main components here are AWS S3 or Backup Vault for storing AMIs and snapshots, or AWS Backup with Storage Gateway, which handles incremental snapshot creation and transfer to AWS. AWS DataSync, which periodically syncs data from on-prem storage to S3 or FSX, and VPN connectivity, which provides secure access during recovery events. Because resources like EC2 instances are only spun up during a disaster, you avoid paying for compute while systems are idle. Ongoing costs primarily come from storage, S3, FSX, or EBS snapshots, and data sync transfer charges. If the data is synced to S3, recovery takes longer and incurs extra data transfer to FSX during failover. Syncing directly to FSX for Lustre is slightly more expensive in storage costs, but recovery is faster and also file level security can be preserved. This design achieves around 4-hour RTO and RPO at a fraction of the cost of continuous replication. It's ideal for workloads that can accept some downtime but still requires a reliable and secure recovery process. Now let's talk about Tier 1, the high availability design for mission critical systems. Here the major cost driver is elastic disaster recovery service. DRS continuously replicates data at the block level from on-prem servers to AWS, maintaining an always ready staging area on EBS volumes. During normal operation, you pay for EBS storage in the staging area, data replication traffic from on-prem to AWS, data sync cost for keeping shared storage in sync to Lustre every 15 minutes, and optionally direct connect bandwidth charges for low latency replication and recovery access. When a disaster occurs and EC2 instances are launched automatically by TRS, compute cost spike, but that's only during failover or testing. This model achieves near real-time RTO RPO and delivers true near real-time recovery. But because the application and storage are continuously active, it's a higher cost option. So to summarize, Tier 1 is a continuous application, low RTO RPO, higher ongoing cost, and driven mainly by EPS, DataSync, Direct Connect, and DRS staging storage. Tier 2, which is AMI backup based, scheduled replication, higher RTO RPO, much lower cost, mainly S3 backup and DataSync expenses. The key point to remember is that disaster recovery is not one size fits all. Strategy should always balance recovery, speed, data integrity, and cost efficiency based on how critical each workload is for the business. Some special callouts is, why not just use DRS for everything? The answer is cost and practicality. DRS continuously replicates data and maintains staging infrastructure, which is excellent for mission critical systems, but not cost effective for non critical workloads that can withstand a few hours of downtime. Also, DRS handles only local block volumes, not shared NAS storage. For shared data, we use AWS DataSync to replicate NAS or on-prem file systems to FSX for Lustre. So, in conclusion, DRS is for critical workloads that demand fast recovery and high availability. AMI based or backup driven DR for non critical workloads that can accept downtime but need cost efficiency. In the next video, we will look at how to automate the entire DR workflow, including replication, failover testing, and monitoring. So that brings us to the end of this video on designing a disaster recovery solution from on-prem to AWS. I hope this video helped you understand how to plan a DR strategy, balance cost versus performance, and choose the right AWS services for each workload type. If you had like to cover any other business problem or architecture scenario, please leave your suggestions in the comments below. I would love to hear what challenges you are working on. Thank you very much.